today I'm going to talk about something which is basically in the middle between coding theory and cryptography. So this is the outline of my talk, and given also the time, I will keep it very high level, so no details. I really want to explain to you the problem we are facing, hoping that some of you may find it interesting and start working on it. So that's the outline. I will give some basic notions about post-quantum cryptography, error correcting codes, code-based cryptography, and the Michaelis framework. Then I will tell you something about BIKE, which is a very good scheme, and it almost became a standard, but it didn't because of an issue that we will see here. And finally, this is the less interesting part, probably. I will tell you something about recent results, but there's a lot to do. So yeah, probably the first three sections will be much more interesting. Okay, so let's start by recalling post-quantum cryptography. So that's something we have already seen somehow. I don't need to speak a lot about it. We have two users, Alice and Bob. They want to speak and using cryptographic schemes, but they can use only classical devices. So like a classical laptop, a smartphone, whatever. Attackers can use quantum computers, so they can run quantum algorithms. We know that quantum computers will appear at some point in the future. We don't know exactly when. However, we know that at some point, I mean, cryptographers are very paranoid. So for us, quantum is now. So we are very afraid about quantum computers, and we are developing post-quantum crypto systems. And you know that NIST is holding a process for standardizing schemes, which means finding the best schemes out there and writing standards so that people can read the standards and implement the schemes. The idea is to transition to post-quantum cryptography by the year 2035. Right now, we are somewhere in the middle here. We have some standards, some new standards are coming. There's a lot we are doing. There's a lot more to do. Okay, so how can we build a post-quantum crypto system? The idea is that of using hard problems which cannot be solved efficiently by classical algorithms and also by quantum algorithms. And actually, we have some, I would say, many sources for hard problems. And basically, we like to classify problems depending on the mathematical area from which they come. Yeah, so for instance, we can define a hard problem if we're looking for solutions of polynomial systems where these equations are nonlinear lattices, isogenies between supersingularity curves, or more generally, post-quantum group actions, and last but not least, coding theory. And coding theory will be the focus of my talk. And you know, the idea of using error correcting codes for cryptography is very old, actually. It started back in 1978 with this paper from Robert Michaelis. Well, this was a breakthrough. I mean, this paper is only a 2-page paper. It's very famous. It's a very important paper. And it basically changed the idea of, I would say, cryptography. Because in this paper, Michaelis proposed, I would say, a general framework to construct a public key encryption scheme starting from error correcting codes. And for those of you that know Michaelis or the Michaelis crypto system, you may know that like some decades ago, the scheme looked like a very good idea, very good theoretical idea, but not very practical. And the fact is that in this paper, Michaelis proposed to use binary GOPA codes. And binary GOPA codes are not so powerful. Like the error correction capability is not super, I will say. And in the end, the Michaelis crypto system with binary GOPA codes has very large public keys. So you have to transmit these keys, and if the key is too large, that's an issue. Yeah, then people started replacing GOPA codes with other families of codes, aiming to reduce the key size. So the idea here is that if you use, let's say, more powerful code, then your code is more powerful, you can correct more errors, you can use smaller codes, and so you can reduce the public key size. Well, this is true. However, we're doing cryptography, so we shall consider security, right? And for many proposals, we know about polynomial time attacks. I cannot enter into details here, but the idea is that if you start from a code having a very strong algebraic structure, like generalized with Solomon codes, then attackers can exploit this structure to do something. Okay, so for many years, people believed that binary copy codes were the only solution, and code-based cryptography is always associated with large public keys. However, this is not true, because in 2013, if I recall correctly, some people proposed to use quasi-cyclic moderate density parity check codes. And these codes will be the focus of this section, because I really want to show to you that using this family of codes, we can obtain something which is very performing, in the sense that we have very small public keys and ciphertext. So we get a very good scheme, and the name of this scheme is bike. However, there's a little issue, and this little issue is still an open problem, and it's very complicated. And also, it's very simple to formulate, so it's kind of strange. Still, this problem is the reason why bike did not become a standard. Okay, so when I speak about quasi-cyclic MDPC codes, I essentially refer to the family of codes you see here in the slide. So we start from two circulant matrices, H1 and H2. Circulant means that each of these matrices is a square matrix, and you can obtain the whole matrix by using cyclic shift of the first columns. Yeah. We also want a moderate density, which means that if we look at this matrix here, the number of ones should be very small. And to do this, we can start by using a weight which is much smaller than the side. So basically, V is the weight of each of these columns here, and you generate a whole matrix by doing cyclic shift of these columns. And if V is small enough, then every column here has weight V, so the whole matrix is going to be very sparse. A lot of zeros, a very small number of set entries. Yes, so this is our parity check matrix, and then we can define the associated linear code. And the code is called double circulant quasi-cyclic MDPC code. Now, I think you are very familiar with LDPC codes, so low density parity check codes. You may not be so familiar with MDPC codes. Well, the fact is that the two codes are actually the same. There's only a difference, the letter. And the fact is that when we use LDPC codes for communication, typically the density goes in this way. We cannot do this in cryptography because we have security issues, because attackers can find the secret key. So the scientists that propose this family of codes propose to use a larger density to avoid this type of attacks. And for this reason, we say that the density is moderate. Still, the code is sparse, the parity check matrix is sparse, so we can do efficient decoding using LDPC decoding. Now, I think we all know about LDPC decoding. I will go very quick here. We know about many efficient decoding algorithms, and normally we can describe these algorithms in terms of message passing algorithms. So we describe the code using the Tanner graph, and then basically the coding consists in an exchange of information between the nodes. So we have the variable nodes, they send information to the check nodes, the check nodes reply, they process information, and this goes on until the nodes reach consensus. Yeah. Normally, we have some failure probability for LDPC codes, and we use Monte Carlo simulations to estimate the failure probability. For instance, I don't know, you want a failure probability of 10 to the power of -6, something like that. You do simulations and you see if your code and the decoder are good enough. Otherwise, you change something. Yeah. So we have many efficient decoders, actually. Normally in cryptography, we use the bit flipping. You may wonder why, because the bit flipping is probably the simplest decoder. I would say that even students from high school can understand it. Well, the fact is that we want for something that is fast and very efficient to be implemented. So in the end, it turns out that the bit flipping gives a very good trade-off between the error correction capability and the performances. Okay. So now we have all the ingredients, because we have a family of codes, QC and DPC codes, we have a decoder, so we can do a public encryption scheme with these ingredients. So what I'm going to present now is actually a let's say, a simplified version of BIKE. Still, the main ideas are the same. Okay, so we are in the general setting where we are transmitting over a noisy channel. So the idea is that we want to send an information sequence U. However, the channel is noisy and the channel is going to add some errors. We want to recover from these errors. The idea is very simple. We multiply the information sequence by the generator matrix of the code, and we get a code word. Then the code word goes over goes to the channel. The channel is going to add some errors, but then when we receive the code word, the noisy code word, we can decode by first computing the syndrome and then using the decoding algorithm. That's the idea. I mean, this is the standard application of linear codes. And now we want to make a public encryption scheme out of this. So the idea is that Alice is going to transmit U, which is the plain text. And what Alice will do is encoding and then adding errors. So in this case, errors are very important to achieve security, because without errors, obviously, everyone can recover the plain text. And then decryption will just be decoding. So what Bob will do is computing the syndrome, decoding, and then finding the information sequence. Yeah. For this to work, we need a trapdoor, and this is what Bob generates in the key generation algorithm. So Bob will sample a random quasi-cyclic MDPC code, and this is very easy and very efficient because we just need to sample two random circulant sparse matrices, H1 and H2, and then we compute the systematic generator matrix for the code, having this form. You can easily verify that G times H transpose is equal to 0. So G is actually a generator matrix for the code, having H as parity check matrix. Then G is the public key, and H is the secret key. Now, you can show formally, if you like, do security proofs, that in the end, security of the scheme relies on two very well-known security assumptions: the quasi-cyclic syndrome decoding problem and the quasi-cyclic code word finding problem. Now, if we forget about quasi-cyclic, these two problems enjoy NP hardness. They are even hard to approximate, so they are pretty hard. Quasi-cyclicity may make them easier, but right now we don't know about efficient attacks exploiting quasi-cyclicity. And the idea here is that basically we start from a secret parity check matrix. So H is sparse. However, when we compute the generator matrix, basically we lose sparsity because H2 is a sparse matrix, but its inverse is going to be dense with very large probability. So when you do this product, what you get is a dense matrix, and G in the end is undistinguishable from the systematic generator matrix of a random code. So basically, looking at G, you don't see that it is coming from an MDPC code. You cannot use efficient decoding, and you have to solve some hard problem. So you cannot efficiently recover from errors. That's the idea with which you prove security for the scheme. Okay, so now let's see what happened in the NIST competition. In the table, you see a very quick comparison between the three finalists in the first NIST competition: BIKE, Classic McAleese, and HQC. Classic McAleese is based on the original idea from McAleese. So Classic McAleese is using binary GOPA codes. And as you can see, the public key is huge, like more than 260 kilobytes for NIST category 1. NIST was looking for a general purpose algorithm, so something that can be run by standard devices, and obviously this is too much. So okay, let's forget about Classic McAleese and let's compare BIKE and HQC. Well, first of all, we see that BIKE has smaller ciphertext, smaller public keys. It's even faster during encryption. It is a bit slower during decryption. Encapsulation and decapsulation corresponds to encryption and decryption, but we are sending a random session key. That's the only difference. Still, the very same algorithms. So yeah, I mean, if we consider this table, it looks like bike is very good, right? From my point of view, its performances are better than those of HQC. However, as you may know, HQC has been selected as a winner. And the issue is that I'm quoting the NIST report from last year. NIST consider that the DFR analysis for bike is not mature enough. And this is an issue for CCA2 security. So this is the issue I was talking about. And this is the open problem we are trying to solve. So what is this DFR? Well, it is related to decoding failures. The fact is that events of failure, decoding failures, are very dangerous for security. Okay, so when I say DFR, what I mean is this thing, which is actually very easy. So basically, this is the expected failure probability when we sample a uniformly at random parity check matrix for accuracy and DPC code, and a uniformly random error vector with weight t. Then the DFR is the expected decoding failure probability. Now, when it comes to choosing a decoder, normally we want the decoding algorithm to be efficient, obviously. This should be rather fast. And we want a good error correction. Okay, like this. Yeah. It's okay, yeah. Okay, sorry. Okay, so we want efficiency, and also we want a good error correction capability. So this means that the DFR should be low enough. Now, let's see what happens when we consider something that we call adaptively chosen ciphertext attack. So in this type of attack, we give adversaries the opportunity to interact with the recipient of the secret key. So in practice, assume that, to make a practical example, Bob is a server. So Bob is accepting queries from users. In this case, the attacker is free to generate ciphertext. He can send the ciphertext to Bob, and whenever decryption fails, Bob will ask for a repetition, right? So in this case, what happens is that the attacker can learn when decryption fails. And remember that the attacker is generating ciphertext, so the attacker knows everything. Like in our case, the attacker knows the information sequence, he knows the error vector, so he can learn something about the secret key. There are practical attacks exploiting decryption failures to recover the secret key, and to rule out these attacks, we need CCA2 security. And if we want to achieve this type of security, and this is what NIST wanted, the DFR must be not greater than 2 to the power of minus lambda. Now, the proof for this is very complicated, but if you think about it, this is very easy to see. Because if this is the decryption failure rate, then the number of queries from the attacker should be at least 2 to the power of lambda. So this means that the scheme is going to achieve security. Okay, and this is where the issue lies, right? For bike, because bike is using QC and DPC codes. These codes are decoded through LDPC decoders. However, this value is very, very small. I mean, that's negligible. Obviously, we cannot simulate probability which is so low. That's why we need to estimate the DFR using a reliable theoretical model. And this is like opening a can of worms, basically, because you can see that the topic is like very important, and a lot of people have worked on it, and even some participants in this workshop are among the names here. So yeah, we did a lot of works. Our knowledge about QC and DPC codes has improved a lot in the recent years. However, this is not enough, and we still have a lot of open problems and open questions. And if you worked a bit on LDPC codes, you may understand why solving these problems is so complicated. But just to mention some questions we're still trying to answer. We have no idea about the asymptotic error correction capability for QC and DPC codes. So when you choose parameters according to best attacks, you have these relations here. we have no idea if there exists a decoder that can decode with negligible DFR. This is even worse when we consider the finite length regime, because in practice, we are using codes having a finite length. So we really want to know if, for the parameters we are considering, our scheme can decode. No idea. I mean, we have some models, but they rely on heuristics. And can you trust heuristics? Who knows? I don't know, and I don't trust heuristics, to be honest. We don't even know if there are weak keys. I mean, people studied some weak keys, so keys having a somewhat larger DFR. However, we don't know if there are many more weak keys. How can we identify weak keys? How can we reject weak keys? And last but not least, we are still trying to find which decoder we shall use for bike. Because the fact is that I told you we are using, I mean, they are using the bit flipping. However, the bit flipping is, I would say, a family of decoders. So you have a lot of choices, a lot of possibilities, and we are still trying to find the best setting, achieving the best trade-off between latency and DFR. And just to show to you that this is a very timely topic, let me tell you something about a couple of recent works I did with my group in Ancona, in Italy. Because we proposed a new decoder for bike, and I would say it's very promising. I will go very quick here. So we call this BF Max. This has been presented in ISIT last year. So it's a very simple variation of a bit flipping where we flip a unique bit, the bit having the lowest reliability. Yeah, we can show that it is inherently constant time, efficient, a lot of good properties, and blah, blah, blah. And this year, we submitted a follow-up of this work to ISIT, where we make use of some trap-in sets. So for those of you that know about LDPC codes, you know that trap-in sets are very hard to find, to avoid, etc. In the case of QCNDPC codes, we can easily identify a family of trap-in sets, and using them, we can essentially improve decoding with a little modification, having, I would say, a negligible impact on performances. Yeah, this is a bit technical. I cannot enter into details, but if you want to know more, just reach out to me. And just to show what's happening here, yeah, so as you can see, this is the computational complexity for our decoder, and I'm comparing with the complexities for the decoders used by bike in the NIST competition. You can see that our decoder is faster. And when we consider numerical simulations, so here we have the DFR as a function of the number of errors. These are the colors are very ugly still. This is the curve for our decoder, and the DFR is always smaller than that of the decoder used by bike. Yeah, so I would say this is a promising decoder. We are still studying it. Still, we are not able to prove that its DFR is negligible. So the problem remains open, and there's really a lot to do. I know, I'm about to conclude. Yeah, so that's my last slide, essentially. What I want to say is that, okay, we have some standards for NIST, by NIST, but they are not the final standards. We are still working to find new schemes. So things may change, and bike is exactly one of these schemes. And moreover, we are really seeking for help by experts in coding theory and communications, because we have this problem. I think it's very funny, also very frustrating, actually. So if you like coding theory and you want to start doing some cryptography, this may be a very good problem to study. Moreover, if you want to know more about cryptography, especially code-based cryptography, you may join us in these two events. So the first one is happening in a nice place, which is close to my city. And this is an informal workshop on the use of group actions in cryptography. And isogenies are an example of group actions. This event is happening in Rome, and it is the international workshop on code-based cryptography. So both workshops are very informal, a very good place to exchange ideas and to learn something. So if you want to join, everyone will be super happy. And that's the end. Thank you very much.
Yeah, thank you for the talk. Is there a question?
Thank you for the nice talk. I'm afraid maybe because it's evening, I didn't understand something. Could you please repeat what is the meaning of lambda? Does it mean that DFR probability of DFR is less than 2 to the power of minus 128?
Yes. Yes.
But it's first of all, it's extremely low probability.
Yeah.
It's and unimaginably low.
Yeah, but so the fact is that lambda is what we call security parameter. So the idea is that a scheme achieves lambda bits of security if all attacks we know about take at least 2 to the power of lambda operations.
Mm-hmm. And in your plot, could you please show the what I also didn't understand? One of the last slides with your plot with the.
You mean the simulations results?
Yes. Yeah. So here DFR is not 2 to the power of minus 100. It's much higher.
Yeah, indeed. I mean, that's why I said that we can see that for what we are able to simulate, this decoder is going better than the other solutions, but we cannot prove that it is better, and we can also not prove that the DFR achieves the desired value.
Because it's written in the caption, it's written that lambda is parameters are such that DFR must be 2 to the power of minus 128. But actual DFR is much higher, so it looks like a contradiction.
Yeah, so I went a bit fast here. I'm sorry. So the fact is that security depends also on the number of errors, and if you want to achieve 128 bits of security, the number of errors is 134. So it is outside of this graph. Okay, so the idea is that if you, I mean, you can guess that, okay, the DFR is going to be super low, but still we are not claiming that using this decoder we achieve security, because we cannot prove that the DFR is indeed negligible. That's the only thing we can say. Like, okay, we did simulations, apparently it's better.
Okay, thank you, very interesting.
Yeah, so there is still a lot of time for questions, but first of all, let's thank the speaker again.